I'm going to be talking about carbon capture and storage, and you may have noticed that this is the only fossil fuel talk. We did have a chapter on that, but we were unable to bring them here. So I'm in some ways substituting for that, particularly in the area of stationary sources of CO2 emissions. So here's the list of the lead authors for our chapter. We had a great team from all over the world, blending academic, NGO, and industry experience. So the way I'm going to do this is I'll just basically go through 13 key findings from our chapter. The first and most straightforward being that the emissions of CO2, the most important long-lived anthropogenic greenhouse gas, can be reduced by CCS. And I'm sure you're mostly all familiar with carbon capture and storage and technology, but for those of you who aren't, it basically involves 4 steps. The capture of carbon dioxide from the smokestack of a power plant or other industrial facility, the compression of the carbon dioxide into a liquid, putting it into a pipeline or possibly on a ship for transport to a location where it's injected deep underground for permanent storage. CCS is applicable to many stationary CO2 sources, including power generation, refining, building materials, and the industrial sectors. I think too often we overlook the fact that this is a broadly applicable technology, and it's often thought of as synonymous with clean coal. But I think certainly as we look to the future, that's far too narrow a definition. On this chart, I also show some interesting data looking at coal use on the left-hand panel, showing rapid increases in coal use, particularly in China, as well as significant growth in India, somewhat slowing of growth in other areas. And second panel on the right, natural gas usage, showing the United States with big increases in gas usage, India, Japan, China, and so forth. So as we can see, there are significant sources of increased use of fossil fuels, and if we're going to be able to achieve the needed emissions reductions, finding a direct way to tackle these emissions is going to be necessary. The interest in CCS has grown very rapidly across the world. I'm probably one of the earlier people to get engaged with this. I began working in 1998 on this topic, and I must say when we first started, I thought of this as very much of a research endeavor, but what we quickly saw is that governments and industry around the world really jumped on board with this technology, primarily because it could deal directly with emissions reductions from the fossil fuel sector. Today, if we look, there are 8 projects in operation with CCS. There are another 8 projects which are called in the execution stage, those projects being under construction and having a very high probability of being operational within the next several years. Moving over to the left, there are also a significant number of projects in the definition stage, the evaluation stage, and those projects also just identifying the potential. So that's where we stand today, and I'll say a little bit more about those trends as we go on in the presentation. So with regard to the technology is basically available today, but significant improvements are needed to support worldwide deployment. For example, with regard to the capture of carbon dioxide, there are 3 different and competing technologies that can be used. We can use post-combustion capture, we can use pre-combustion capture, and oxy-fuel combustion, each of which has the potential to achieve the needed removal of CO2 from the smokestack of a power plant or industrial facility. With regard to options for storing CO2 in the subsurface, we can put carbon dioxide into depleted oil and gas reservoirs, including the potential of simultaneously increasing the production of oil and potentially even gas at the same time. Combining CO2 storage with enhanced oil or gas recovery has the benefit that you can offset the costs of the capture, which are significant today. It's also possible to put carbon dioxide in deep saline formations, which could be both onshore and offshore. And finally, there's some limited potential for storing carbon dioxide in coal beds, also potentially in conjunction with enhanced recovery of coal bed methane. So with regard to the needed technology improvements, these are listed here. First, with regard to capture, the primary need is to reduce the cost of capture. Today, if you add capture to a power plant, a coal plant, or a natural gas plant, the cost of power generation would go up by about a factor of 1.5 to 2. So significant cost reductions are needed. As an important part of that, capturing carbon dioxide requires a lot of energy, primarily in the regeneration of the solvents that are used to capture the carbon dioxide. Today, up to 15 to 30% of the total power output of a plant may be required in order to capture carbon dioxide. And the final area where we have much less experience has to do with the integration of the power generation and other applications with the carbon capture technology. Within the area of storage, there are two primary needs. The first is to increase confidence in the permanence of saline aquifer storage. That involves learning how to select sites in a reliable way and to monitor the project over the lifetime of that project to ensure conformance with the performance standards. The second issue is something that's emerged more recently regarding the potential to induce seismicity associated with the injection of carbon dioxide in the underground. This is a well-known issue with regard to injection of fluids in the subsurface, and it's traditionally managed by limiting the rate of injection so as to keep the pressure buildup below a specified level. And certainly a similar approach will work here, but given the potentially very large scale of injection, it will be important to get a better handle on those maximum pressure limits that are tolerable, and also recognizing that they'll be geographically specific. So having said that, though, there are 9 ongoing projects. Sorry, this says 5 in this chart. There's actually new stuff happening, and I did update this graph from the GEA report. And basically, these 9 projects are operating successfully, demonstrating that CCS can be safe and effective for reducing emissions. If you look at this chart, the first project was at Sleipner project in offshore of Norway, about 1 million tons per year. That's been going ever since. Moving on from that, the Weyburn project in Canada, then the Insala project in North Africa, the Snøhvit project, Decatur, Cranfield, Citronelle, and Port Arthur. So today we're injecting about 10 million tons per year of carbon dioxide underground, specifically for the purpose of carbon dioxide capture and storage. This does not include about the 50 million tons of carbon dioxide that are injected every year for the purpose of enhanced oil recovery. And by and large, these projects are going well with extensive amount of monitoring and regulatory oversight to confirm that they're performing as expected. The next conclusion is that significant scale-up compared to the existing CCS activities will be needed to achieve large-scale reductions in CO2 emissions. A 1,000 megawatt coal-fired power plant will create about 8.5 million tons per year of CO2 emissions. That's comparable to the largest of the large-scale injection. The LaBarge project is about 6 million tons per year. So that's comparable to that. But if we were, for example, to want to achieve 100 or 1 gigaton or 1,000 million tons of CO2 removal from emissions, we would need to scale up the existing activities about 100-fold, which would be comparable to about 120 coal-fired power plants. With regard to the technical potential of CCS, on a global level, it's very promising, but on a regional level, it is differentiated. What that means is if you look at this map of the globe, you'll see those areas that are in dark gray or in the middle gray tone. Those are areas that are considered to be prospective for CO2 storage, and you'll see that some areas in North America, the Middle East, Russia, North Africa are particularly well endowed with CO2 storage prospectivity, but some areas, notably India and certainly parts of China, are lacking the potential for CO2 storage. So capacity estimation has been one of the largest challenges worldwide because this was not information that was available a decade ago. So many governments have undertaken very systematic studies to identify the storage capacity. However, much more experience is needed. In particular, we need to so-called do the experiment, meaning we need to test if in fact that capacity is actually available. So I show two panels here. On the left-hand side is a panel showing what is known about the potential storage capacity in oil and gas, saline aquifers, and coal beds with both high and low ranges. You can see by far the largest potential capacity is in saline aquifers, but also the range is quite large. And even though the oil and gas wedge there looks quite small, in fact, that would be sufficient for at least 100 years, or for 100 years, 50% of all the needed sequestration that is imagined to be done over the coming century. So it's quite large. Looking to the right-hand panel, again, you can see for various regions of the world the current status of knowledge of capacity. North America, again, is very large. Some studies suggest that China, though not having evenly distributed capacity, also has quite large a capacity. Having said all these things, going back to Diana, sort of the good news and the bad news is that the bad news is that the combination of high costs of CCS and absent or low incentives for large-scale deployment are a major limiting factor for the widespread use of CCS. And here we see the cost of, or the price for emission trading credits in the European, the ETS. And you can see whereas they started about $30 per ton of CO2 in 2008, they're now down at the range of several dollars per ton. This is far lower than the estimated $30 per ton that would be needed to actually incentivize investment in CCS projects. With regard to environmental risks of CCS, they appear to be manageable, but certainly regulations are needed. In particular, it is important for governments to develop standards for acceptable risk, to lay out regulatory requirements, which will be then transferred into a design basis for a project, in particular site characterization and selection criteria, procedures for dealing with active and abandoned well completions, and finally, the implementation of storage engineering to make sure that a project conforms. Having said this, I'll also say that over the past decade or so, particularly since the IPCC Special Report on Carbon Dioxide Storage and Capture was done, there's been a recognition, though, that over time, the risks of geologic storage will actually decrease. So it's possible to design your project so the maximum risk is actually during the operational phase of a project when you have active monitoring and ongoing oversight. So with regard to implementation, experience has so far shown that local resistance to CO2 storage projects may lead to cancellation of planned projects. And I will say the reception to CCS projects has been very uneven. There are many examples of positive reception in the United States, though there have been other examples where there's been some resistance. But particularly in Europe, there's been quite a concern about these projects in the Netherlands and in Germany, and the kinds of concerns stated are local concerns about safety and health risks, but also general concerns, including the diversion of attention from renewables and efficiency gains. At the end of the day, social, economic, policy, and political factors may limit deployment if not adequately addressed. In fact, we could have an excellent technology, but unless we have early adopters to help begin moving down that learning curve, unless there are business models that compensate those involved adequately, unless there's public support, policy support, dealing with land use issues such as, for example, who has the right to put carbon dioxide in the pore space under your land, dealing with issues of long-term stewardship through institutional means that provide assurance that if something were to go wrong long into the future, that it would be dealt with appropriately. Regulatory capacity, particularly in the developing world, is important. And finally, if we don't start doing this at scale, we're not going to be able to take advantage of learning by doing, which we've seen in every other area has been so important towards pushing those technologies over the threshold where they become economically viable. And we also heard this earlier, but that CCS combined with biomass has also the potential to lead to negative emissions. And in this chart, this is a chart actually Naki showed earlier, showing many of the GEA scenarios. And what you'll notice that there are many pathways that go below the zero mark, meaning negative emissions are required. And today, CCS is really the only technology, CCS combined with biomass or direct capture from air, is really the only way we know that we can do this at scale. So I'd like to close with some remarks about the consequences of excluding CCS from the mitigation portfolio. In particular, integrated assessment studies suggest that the overall cost of mitigation will increase if we do not include CCS in the mitigation portfolio. Second, sufficiently large emissions reductions will not be possible without CCS. In particular, baseload and peak load generation will be challenging without fossil fuels. Third, political support for mitigation will be weak. Fossil fuel-rich regions of the world will will resist mitigation if they don't see a way for them to participate in the overall solution. And then finally, there will be some geographic areas that will not be able to reduce emissions rapidly enough because the renewable energy or nuclear power options may not be available to them. So with that, thank you very much.